Okay, look up. Okay, so quick reminder. Make sure that as we're discussing today, you are not trying to just wait to like do what I do. Like you're trying to make sense of the idea. Really limits. Once you make sense of the idea, solving the problem becomes relatively straightforward. So we talked last time about the idea that we're just dealing with a big set of XY pairs. When we look at a graph, we're just looking at a bunch of dots where every dot represents an XY pair. If we try to find something like this, like if we see this kind of an expression, it says f of, we'll just use 3 is fine. And get the pen to work again, sorry. So if we use, come on. So if we say f of 3, that's simply asking us, this is frustrating, sorry. It says f of 3, we're paying attention to this exact xy pair. We're looking at an x coordinate of 3, and we know the y coordinate that goes with it is exactly 1. When we talk about a limit, well, we haven't talked about that yet. So this is where we started, yes? I think that's how far we got. Let's jump to this page. Each class kind of stopped at a slightly different place. I believe we talked through this as well. Nod is good.
Yeah.
Okay. Did we start here at all?
Yeah.
A little bit? We're going to kind of go through this again. Okay, so I just wrote down the idea, and I'm going to use this graph right here to say it one more time, that when I write this symbol, I say f of b. This is a y coordinate whose x coordinate is b. So here's where the x coordinate's b. I look on the graph where the x coordinate is b and I find one dot here. We're going to say that dot has a y coordinate of 3. So we know that f of b has a value of 3. This symbol represents a y coordinate. This is a y coordinate. And it's the y coordinate that goes with an x coordinate of b. And the pen is just not my friend. So, question? And again, you don't really have to have a question in my class. You simply have to have that feeling of like, oh, I need to hear that again, or just any thought that pops to mind. Don't hesitate to raise your hands. Cool. Okay, the new idea for calculus is the idea of finding a limit. But if this makes sense to you, this idea that f of b is exactly 3, then finding a limit really isn't that difficult, because we're still just dealing with x and y coordinates. If we make a little table here again, the only difference is that when we're finding a limit, we don't allow the x coordinate to actually equal b. So here, the x coordinate is precisely equal to b. But with this expression, the x coordinate is never going to equal b. The x coordinate is going to get close to equaling b. The x coordinate will never actually equal b. Thoughts or questions at this point? So again, if you just keep track of the two different cases, it's pretty simple. This symbol, x is exactly b. This symbol, just like the symbol indicates, it doesn't say x equal b. It says x is getting close to b. So when we're doing a limit, this is what we're doing. Now, if you look at the graph, there's two different places where the x coordinate can be almost equal to b. there's only one place where the x-coordinate can be exactly equal to b. That's right here. But if the x-coordinate is slightly less than a value of b, then we would be, it's really hard to draw, so you have to kind of imagine, but instead of looking right where b is located, we would be looking just barely to the left. Like we'd be looking at the x-coordinate that's just to the left of letter b. And we use a symbol to represent that. We say that we are slightly negative of an x-coordinate of b. So this is likely a new symbol you haven't seen before. It doesn't represent exactly b. It represents slightly less than b. Questions? Thoughts? Anything? Please.
Can you use that minus symbol for a number or is it only letters?
Perfect. Take two tallies, mark them down. Jonathan, yes? Okay. Jonathan Hansen. And I'll say your last names for a while just so I can kind of remember them. Then eventually I'll stop saying both your names. So, no, it applies to anything. So B is representing some unknown value, like it could be 2, based on this graph. So no, you can use it with a number. 2 minus is like saying, so if I write 2 minus, that's the same as writing, in fact, somebody knows, like just raise your hand, I'll pay you. What would be the decimal kind of equivalent to this symbol 2 minus, which means just a little bit less than 2, Paige?
Like 1.99999.
Perfect. So the idea of 1.99 forever, which is kind of a weird idea, but that's the idea. You're trying to pick the value that is infinitesimally less than 2, just by just the smallest amount you can possibly imagine. So mark down 2 tallies, Paige. Paige, all right, okay. Other thoughts? The other way to get close to b is, of course, to be slightly more. So that would look like this. And on a graph, we'd be looking, again, it's difficult to draw, but we'd be looking like right here. And not a really tricky concept, but I just want to pay some extra credit. So somebody raise your hand and tell me if we're looking at a value like 2 plus, what are we looking at? Working on names still. Shoot. No, not yet. Jacob. There we go. Go ahead, Jacob.
Wouldn't it be 2.00 all the way to infinity 1?
Mm-hmm. Again, it's not really possible to write that, but as long as you can conceive of what we're talking about, you're right where we want to be. So take down 2 tallies, Jacob. So again, the x-coordinate is exactly b, the y-coordinate is exactly 3. When we're finding a limit, we are not going to have the x-coordinate ever equal b. It's simply going to be close. But you can't forget there are 2 ways to be close. There's slightly more than b and slightly less than b. And limit is asking you to figure out, just like you did here, when the x-coordinate is exactly b, what's the y-coordinate? When the x-coordinate for this set, remember, this isn't a graph, it's really just a bunch of xy pairs. For all those xy pairs, when the x-coordinate's just a little less than b, what does it look like the y-coordinate is getting really, 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 really close to becoming? Or maybe it's better to start out with, like, what is the y-coordinate when the x-coordinate is just a little less than b? I'll pay everybody to raise their hand on this one. So look here. Remember, you're just looking at a bunch of dots. When x was exactly b, the y-coordinate was exactly 3. So I'll pay everyone who raises their hand. When the x-coordinate is slightly less than b, what y-coordinate corresponds to that x? Like it's a single dot. It's not really, but it's we imagine that we're looking at one dot. That dot has this x-coordinate, and what's the y-coordinate? That's what we're looking for. Just waiting for everyone to think for a second. If your hand isn't raised, talk to the person next to you and see if you can make sense of it and raise your hand as well, because I'd really like to get more extra credit. Okay, show me your hands. What do you got? Who's ready? If you don't raise your hand, don't take extra credit. I do want to pay as much as I can. Show me your hands. Who's ready to tell me? When the x-coordinate is slightly less than b, so come back. You gotta stop doing that. When the x-coordinate is slightly less than b, what y-coordinate are we seeing? Show me your hands. Stop talking up. Show me. Oh, you're doing really good thinking. Keep your hands up. Hands up. Hands up. What do we got? Let's go. Miles Pavia. What do you see?
We thought it would be 1+.
So you're looking. I want to make sure you and I are looking in the same place. The dot we're looking at, or at least we imagine we can see, is a dot that would be like right here. Best I can draw with this really bad pen. Does that make sense? Raise your hand if you were looking right where I drew. Show me your hand. Mark down 2, please. Give 3 for Miles. Questions? Oh, please.
So we were just kind of confused why you did, when you first did f of b with 3. Why was it 3 and not 1?
Okay, no worries. I'm going to do my best to explain it. If it doesn't make sense, you just keep talking to me. So, a whole bunch of dots here. When I write f of b, I'm looking for the dot whose x-coordinate is exactly at b. So I basically say everywhere along this dotted line, the x-coordinate is b. But the only dot that is located along that line is right here. And that dot has a y-coordinate on the scale I drew of 3. And that's why when the x-coordinate is exactly b, this y-coordinate is exactly 3. I don't know if that helped though. Talk to me.
Sorry, so like the open dot that's on one right above B, is that just not counting your point because it's like open?
Yeah, stay with me, Emmy. This is going to sound like a stupid question, but I hope it helps. Is there a dot right here? No. Is there a dot here? No. The open circle represents the fact that there isn't a dot. So you don't even look there at all. Like when I look up and down the dotted line, I go, oh, there's nothing here, there's no dots here, there's no dot there either. Oh, there's where the dot is located. Did that make sense?
Yeah.
Take down 3. Question. I said something funny by accident. You good? Okay, just making sure. The purpose of the open circle, listen, the purpose of the open circle is not to locate what's at the open circle, because nothing is there. The purpose of the open circle is to be able to identify the red dot. And to say, oh, I can tell from the graph that that red dot is slightly more than 1. Like infinitesimally more than 1. 1.00 forever 1. Questions? Cool. What goes here? Hands. I'll pay everybody. Anyone raises their hand gets paid. Don't take payment if you don't raise your hand. I trust you to be honest. So, Zarin King.
1 with a minus.
Perfect. So I'm looking right here. Being hard to draw, but that blue dot is where my eye is drawn when I'm thinking of an x-coordinate that is infinitesimally greater than b. And sure enough, the y-coordinate that matches up with that dot is a y-coordinate that's infinitesimally less than 1. So show me hands again who had their hand raised a minute ago. Take 2, Zarin, take... Sarah's over here, take 2 for my bad name. Now you're saying, shoot. We'll just pay both of you and call it good. Sorry, Ryan, my bad. Everybody else take 2 tally marks. Okay, look. Look here. Look here. Okay, remember, limit means think about the x-coordinate that is infinitesimally less than b, but also think about the x-coordinate that is infinitesimally more than b. Look at the y-coordinates that correspond to those x-coordinates and say, oh look, when the x-coordinate is getting infinitesimally close to b, the y-coordinate is getting infinitesimally close to 1. Because on one side, the y-coordinate was just slightly more than 1. On the other side, the y-coordinate was slightly less than 1. So if I get closer and closer to an x-coordinate whose value is b, I will be getting closer and closer to having a y-coordinate whose value is 1. It's not until I get to exactly x equal b that the y-coordinate changes suddenly to 3. So the key is to notice the difference, because that's what they'll test you on, is knowing that this is what happens when x is exactly b. This is what's happening when x is never exactly b, but infinitesimally close. Question? Awesome. So here, just another example. The x-coordinate's getting infinitesimally close to equaling 3. So if x were exactly 3, y would exactly be 1. But if x is only close to being 3, so I have my little table again. If the x-coordinate is slightly less than 3, my I would be drawn right here. Hello. Computer's talking to me for some reason. And I would note here it's a little bit different. The y-coordinate isn't close to equaling 1. The y-coordinate is 1. So as the x-coordinate gets closer and closer to equaling 3, but it's just a little bit less, the y-coordinate, because this is a horizontal line, that y-coordinate is just staying at 3 the whole time. On the other side, I would have slightly more than 3. And just because I like paying extra credit, hands up what goes here. Okay, everyone who raises their hand. Plus it gives me a chance to practice names. Well, Emily Nava. Yeah, wait, that's right. Perfect. And because I'm lazy and don't want to write it all the way out, no, it's perfect. It's perfect. Either way is fine. It really is. Because in reality, Emily, they're never going to test you on this. This is just your thinking. They're going to test you on this. They want to know if x gets really close to equaling 3, what do we observe the y-coordinate doing? We observe the y-coordinate getting really close to 1. Okay, 2 points, 3 for Emily and Henry's. Oh, please, David.
Why do you guys do that if there's already a point there? Like, you notice that there's not a force graph. So why do you care about the graph?
Perfect. Take 2, David. They will typically not ask you to find a limit at a location like this, where nothing interesting is really happening. That's not very common. It's much more likely that they'll ask you to find a limit like here, where there's a vertical asymptote, or here where this is called, in a previous class they called it a hole. On the AP test you have to use the word removable discontinuity. Whatever. I don't know who came up with that idea. It seemed like 4 letters was a lot better than 2 long words, but anyway. So this is known as a removable discontinuity. That's common for them to ask for a limit there, just like we did up here. this is a jump. Yeah, this seems so nice. You know, jump has 4 letters, whole has 4 letters, but whatever. I don't write the test, so. But David is correct. Not likely to ask a limit here, but I thought it important to show you that you can. Doesn't mean they will, but they could, I suppose. Does that answer your question? Okay. Anybody else? Oh, please.
Is there like a certain way to say what's on that, on your little table there? Like is it just 3 plus and 1 plus and 3 minus, or how would you say that?
Yeah, just exactly, just like that. So no, it's perfect. And again, this is scratch work, so this isn't the kind of thing the grader's ever going to grade you on. So you would never turn in this like, oh, here's my work, kind of a thing. And a problem like this, they don't expect to show any work. They just want to see the answer. But yeah, you just say 3 minus and 3 plus, even though what it means is infinitesimally less than 3 and infinitesimally more than 3. You don't have to say all that. So, does that make sense?
Yeah.
2 tallies. Anybody else? Oh, please.
You're saying like they just want an answer, but for a question like this, what would you have like your answer be notation-wise, like as a coordinate pair for both of them? Or?
Gotcha. So this again is what you want to be thinking. And then when you're thinking this, you're saying, okay, so what you see, most likely a multiple choice question, to be honest. Never seen a written one that's like this. They'll just have a picture of the function, and they literally will just have this. Oops, that's a 3. Sorry, Daniel. Hold on. Pretend that, there we go. So they'll just have that, and you do this thinking, and you say, oh, when x is getting infinitesimally less than 3, or x is infinitesimally more than 3, yeah, the y coordinate is getting infinitesimally close to equaling 1. Even though, in this case, the y coordinate never really does equal 1, limit is asking you to identify, what am I getting infinitesimally close to equaling? Does that make sense? 2 topics. Awesome. Next page. Okay, we've already talked about it. You can't forget, there are 2 ways for an x-coordinate to be infinitesimally close to equaling some number. You can be infinitesimally more or infinitesimally less. They do give names to that. When we are infinitesimally less, we refer to that as the left-hand limit, just because as you look at the graph, you're on the left side, you're infinitesimally less. Infinitesimally more is the right-hand limit. And you must know this notation right here. They will test you on that notation. So even though I said a minute ago that they're not going to be looking at a table and paying attention to your little notation like this, this is not considered, I don't know, like clean mathematically. It's just kind of scratch work. This they do expect to see. And you will get tested on that in the written section. Jacob Jackson, please.
As you're writing that, do you have to write the x arrow v minus as you're writing the lim f of x or whatever?
Yeah, you do. I'll show an example of where you would have to write it in a minute, but yeah, perfect. 2 tallies. No worries. Anybody else? Pretty good. Okay, pay attention to this word. Must. Whenever you see this kind of a statement, the limit as x approaches b or whatever number, you must immediately remember you cannot answer this question without first answering this question and this question. It's not possible. I can't answer this ever unless I check the left-hand limit and the right-hand limit. Question. Please.
So, why do you need to find the left hand and the right limit? Like, we did that in the last problem when the dot was just like the 3, and you could see that right off the bat. does that mean you still need to find the left-hand and the right-hand limit first?
You said it perfectly, Zarin. Like if I'm looking at this graph and I'm being asked to find the limit as x approaches a, and this is a multiple choice question, your brain should automatically think, oh, I just need to check a little less than a, a little more than a. Right there, you've done this. Like you're checking both of them, you're just doing it mentally. So multiple choice, you don't have to write anything. You just, your brain looks at that and says, oh, okay, so the x coordinate is slightly less than a, then I'd be here. The x coordinate is slightly more than a, I'm going to be here. Oh yeah, look, as x gets really close to equaling a, the y coordinate is getting really close to equaling 2, even though, let's pay the whole room for this one. If you're not exactly sure what word to use, that's okay. So this is what happens when the x coordinate is infinitesimally close to equaling a. The y coordinate will be infinitesimally close to equaling 2. The y coordinate won't ever equal 2. What do I write here when the x coordinate is exactly a? And what do I write here when the x coordinate is exactly a? 10? Undefined. I'll just abbreviate that. Because when x is exactly a, there isn't a dot anywhere. So there's no y coordinate for an x coordinate that is equal to a. Getting used to a new board, so. Hello. The board is having trouble recognizing the difference between the pen and my hand for some reason. There we go. Question, 2 for 10. Oh, please.
I'm just assuming you can still write NA or not applicable as well, or no? Not in this case.
On a I'm just searching for your name again, sorry.
Jackson Sanders.
Thank you. Say it one more time.
So can you still write NA for not applicable, or in this case, does it have to be undefined?
On a multiple choice test, the only answer that they'll have that's valid will be undefined. Like they won't have one answer that's not applicable, one answer that's undefined. They'll just say undefined. On a written test, you'd have to write undefined. Just the rules of the test. To me, a common sense answer is NA, but they won't accept it. So, tell me your name one more time.
Jackson Sanders.
Jackson Sanders. Thank you, Jackson.
Just another syntax question. What if you're like DNA does not exist? Is that?
Gotcha. David Gardner, right? Edward Gardner. For whatever reason, and I don't have a really good answer for this, it's simply the language they use. When identifying the value, the y coordinate, for an x coordinate where there is no y, they always expect you to use the word undefined. When identifying the value of a limit, if the limit is non-existent, we'll use the words does not exist or non-existent. But we won't cross those out. Like this one, we'll just always use undefined. Limits, we'll always use non-existent. 2 talents. Anybody else? Cool. So here, in fact, let's do this real quick. Feel free to talk to each other until you're confident you have this correct. What number do I write here? Hands, please. So here's my graph. Trying to find the limit as x approaches b from the left, which means I'm identifying when the x coordinate is infinitesimally less than b, what y coordinate am I getting infinitesimally close to? Looking for a hand. Feel free to talk to each other. I want to pay as much extra credit as I can. Okay, show me your hands. Who's got it? Don't take points if you're not raising your hand. So Jack will repulse.
It'd be plus for B minus.
So, here's what Jack is thinking, and you are absolutely correct. In terms of x and y pairs, for this set of xy pairs, if I have an x value that is slightly less than b, I'm definitely going to have a y value that is slightly more than 2. Raise your hands if you would have said that. Take 2, Jack will take 3. When it comes time to answer the limit, one subtle difference. The word limit means what y value am I getting infinitesimally close to equaling? Well, if this is the actual y value, then I am certainly infinitesimally close to 2. And because we do not study limits at extreme depth in this class, they've never asked a limit question where the answer doesn't come out to be something nice and clean. Like, they don't expect you to pick up your calculator and figure out that the limit is 1.57. They're going to have answers like 2, -5, maybe 1/2, but it'll be clean. So the answer to this is 2. The left-hand limit's value is 2. Question? Awesome. Raise your hand and answer this one, please. Show me your hand. What goes there? Wow. Oh, sorry, my bad. I looked at Brinley and said your name, so I apologize. Sorry. Brinley, go ahead.
One, but would it be one positive? Or is that just for the?
Yeah, no, your thinking is perfect, Brinley. Over here, when b is a little bit, we're just infinitesimally more than b, we're definitely looking at a y coordinate that's just slightly more than 1, because our eye should be drawn here, which means in terms of a limit, we are getting infinitesimally close to exactly 1. So when you answer a limit question, you don't ever put a plus here. They won't give you points for that. But thinking, that's what you should be thinking. You're slightly more, but you don't put the plus on the limit. How many knew it? 2, 3 for Brinley. So. Question? Okay, cool. And this is what, it was David brought this up, right? Edward Gardner. There we go. The word non-existent, correct? Okay. So, okay, remember, when you're asked to find, I call this the overall limit. Okay? When you're asked to find the overall limit, don't. You must find the left and the right. And if the left and right are not the same, as we see here, then the overall limit is non-existent. Or I sometimes use the abbreviation D&E, does not exist. So I never, ever, ever find this limit. I always find the left and the right and compare them. Always. No exceptions. Now sometimes I do it mentally. Like I don't write things out, I just kind of look at it. I think Sarah was saying that a minute ago, I believe. But I am finding the left and right always. So, question? Oh, please.
What if this wasn't here at all?
Oh, awesome. Awesome. So here's what, sorry, we're working on names at the same time. Paige, right?
Yes.
Here's what Paige already is saying. What if the graph, let me show you one that does exactly what you're talking about, Paige. If you flip forward in your handout just a little bit, you'll see a picture that looks like this. I have a lot more pages because I was leaving space for me to draw. Trying to get right there. So this is 1, 2, 3, 4. Did you find it, Dave? If they were asking me to find the limit as x approaches 4 from the right, I am thinking, well, I've got to find a dot whose x-coordinate is infinitesimally more than 4. But there isn't one. This dot's way too big. I'm not sure why I drew it so large, but that dot is only at x equals 4. If I try to go this way and be slightly more than 4, there's no dot. So that limit simply does not exist. There just isn't anything. Does that answer your question?
Yes.
2 more. Yeah. Cool. So let's go back. Okay. We already talked about this one. If I'm finding the limit as x approaches a from the left, x approaches a from the right, and they are the same, then this overall limit is that same value. That's why this limit in this problem happens to equal 2. Questions? So when the left and right limits are the same, that's the value of the overall limit. When the left and right limits are different, the overall limit does not exist. It's just one of the two. Carl, Robson, please.
It doesn't matter if it's like a 2 plus or 2 minus, as long as they're both 2, it stays, like overall, it stays the same.
Correct. The thinking there is this, Carl. When they're asking me to find that overall limit, I'm trying to, I shouldn't have used 2. I'm trying to identify, what y value does it appear I'm getting infinitesimally close to equaling. And I'm just making up a problem. Well, let's use A, I'm sorry. Oh, come on. You're very patient with my new board woes here, sorry. So in both cases, this one is 2 minus, this one's 2 plus. So Carl's right. The y-coordinate isn't ever actually equal to 2 when we're near x equal a. It isn't. But it is infinitesimally close. In one instance, infinitesimally less, the other infinitesimally more. So we basically say we're surrounding it in a sense. You don't have to surround it, just whatever we're infinitesimally close to. You're good? Yeah. Okay, 2 more. Oh, please.
I'm just double checking my thinking. So if it was, if we were trying to find the limit right at the point of like a absolute value graph or something, and they were, both points were, say, 2 plus, then the limit would be 2 plus?
Good question. Jackson Centers, yes?
Yeah.
Okay. Let's do it right here. I'm going to just draw in some numbers, because I think this is roughly what you're saying. We'll just pretend, based on the scale here, that this is about 5. Is that okay? If I were asked to find the limit, so first of all, I'll just talk with you, Jackson. I think this will make sense. What would you say is f of 5? 3. So when the x-coordinate's 5, the y-coordinate's 3. But if I'm finding the limit as x approaches, I apologize for staying in front of the board, I just haven't really right. Like this, well, I have to think of both left and right. So in my brain, I'm thinking, okay, the limit as x approaches 5 from the left. And just like you said, in fact, what would you write here?
3 minus.
So again, if you're thinking in terms of xy pairs, 3 minus is exactly the right answer. If you're answering a limit, we don't ever want to put the minus. We want to say we are getting infinitesimally close to 3. And then when we do the right-hand limit, that is the right word. What happened? There we go. Sorry. So up here, Jackson, what goes here?
That would be 3 minus.
Perfect. What goes here?
3.
You got it. And because those two are the same, this limit is also 3. Did that answer your question?
Yeah.
Good work. Make sure you take down some tallies for all the times I said your name. So, questions? Just a compliment to the whole room. The way you are interacting is perfect for this class. It is. Like you are asking the right questions. Like you're totally focused on what does this mean versus like what do I do? It's perfect. Okay. Other questions? Oh, please.
What's the point of the overall limit if it's the same as the other two limits?
Gotcha. We don't have time to go into the depth of that question today, but it will come up again and again and again throughout the year. And the idea is that there were mathematical questions that for, honestly, thousands of years, mathematicians said we have no answer until Isaac Newton discovered that we really don't have to know exactly what's happening at, say, 5. If we can figure out what's happening a little less and a little more, and we can get infinitesimally close, it actually is sufficient. It's not the best answer in the world, but that's the breakthrough that he made. So, and calculus is actually based on that idea. So we'll get there, but be patient. And it's Jacob Jackman. Anybody else? Cool. Next page. Okay, this came up, I believe it was David who asked this question, that in our AP Calculus class, when they ask us to find a limit as x approaches some finite number, they're almost always doing it at a point of discontinuity. Like we showed examples that you can find a limit where the function is continuous, and they will sometimes ask that as well, but at a point of discontinuity is most common. So you have to memorize this. 3 different types of discontinuities. And I would memorize them in this order. If you memorize the order, it helps with some of the stuff in the future. So, jump, removable discontinuity, previously known as a hole, or a vertical asymptote. Questions? We will study horizontal asymptotes in association with limits as well, but don't put, it's not a discontinuity, so don't put it in there. So, question? Okay. You need to memorize this statement, number 12. Jumps only occur at the transition points within piecewise functions. You must have that memorized because they will have, it's been very common to have AP questions where they say, hey, does this function have a jump? And they won't give you a graph, they'll give you a formula, and your first thought has to be, is that a piecewise function? If it's not piecewise, no jump for our class. So, if the piecewise function has a transition point at x equal 2, and the left and right limits don't match, that's what constitutes a jump. So you need to have memorized that when we're looking for discontinuities at, say, x equal 2, we're just going to check the left and right limit. If they're not the same, we know there's a jump. So, please.
What's a piecewise function?
So piecewise, we'll get to it in a second, Allison. No, don't hesitate to ever ask. I was just kind of letting you know we'll get there. It's a formula that looks like this, like that. So I think you've seen them in previous classes. It's been a while. So no, don't hesitate to ever ask. That's what you see when you see a piecewise. And the graphs we've been looking at are actually piecewise functions. They're functions that are defined in pieces, in sections. So like there's this section, just different sections. Answer your question? Okay, 2 tallies. Okay, so that's a jump. You need to have that memorized. Left and right limits don't match, that's a jump. Jumps only occur in piecewise. Next thing, item 14. Remember, because you can't find a limit without checking the left and right anyway, so you're looking for what's happening at a discontinuity. You check the left and right limits, they end up being the same. They equal each other. So there's not a jump. But if the left and right limits are one value and the value of the function is different, so it's that comparison between what's happening exactly at, in this example, x equals 0, compared to what's happening when x is simply getting infinitesimally close to 0. Well, if from the left and the right, we're getting close to the same y value, but when we go exactly at 0, we get a different value, that's a removable discontinuity right here. So in this picture, right here at x equal 2, because the left and right limits are different, that's a jump. But over here, the left and right limits are the same, but the value of the function is different, that's a removable discontinuity. Question, please.
So does like a jump kind of superseded this removable discontinuity in definition? So if you have like a line and then a point and then a line, would that be a jump?
Yes.
Sorry,
Yeah, it's perfect, Daniel. That's why the order is important.
Okay.
So we always check the left and right limits, because that's how we find a limit. We first look to see if they are different. If they're different, we declare a jump and we quit. Does that answer your question?
Yeah.
2, that one. So that's removable. And then the last one, at a vertical asymptote, the limit, well, some mathematicians say the limit can be infinite. I prefer the answer that the limit does not exist, which is also acceptable, because I can't tell you, like when x gets close to equaling -1, if x is a little less than -1, the y-coordinate's going to just become increasingly negative. So I can't declare, hey, I'm getting close to this y value. I'm not. I'm growing negatively forever. So the limit is non-existent. So this left-hand limit, non-existent in a negative direction. This right-hand limit, non-existent in a positive direction. Therefore, the overall limit is also non-existent. These limits that grow to infinity, that's what causes a vertical asymptote, the third type of discontinuity. So. Cool. All right. And then the last thing to memorize is what's known as the definition of continuity. So, and it's back to what Daniel said, we're checking things in order. We're looking at a place where there is possibly a discontinuity. So in this example, we're looking at 1. So we find the limit, left and right. They match. In this case, both the left and right limit would equal what appears to be 3. But the value of the function, f of 1 itself, is also 3. So because all three things are the same, the function is not discontinuous, it is continuous. And they will test you on that for sure. So. Question? Awesome. And then the last thing is horizontal asymptote. If we are asked to find the limit as x approaches positive or negative infinity, so like this, the limit as x approaches, say, infinity, for this function f, that's no different than what you previously were told is end behavior. You're just focusing on, hey, when the x-coordinate grows forever, what does the y-coordinate do? Well, based on this picture, as the x-coordinate just keeps going this way, the y-coordinate's getting very, very close to -3. So this limit is -3, and I can declare that there's a horizontal asymptote at y equal -3 for when x is approaching infinity. have to be a little careful because when x approaches negative infinity, something else happens. So the limit, as x approaches negative infinity for this function f, that's going to get really, really close to 2. So that means as x approaches negative infinity, I have a horizontal asymptote of y equal 2. Question? And then one other thing to note, they've tested before, they've said things like, if a function has a horizontal asymptote of y equal -3, they'll ask this question: can f of x ever equal 3? And the function, can f of x ever equal -3? And the answer is it can, because horizontal asymptote simply is describing what's happening as x approaches infinity or negative infinity. So somewhere else on the graph, the value can equal -3. There's no restriction on that. So, okay, next thing. Okay, very quickly, turn to this page and just work together. Just fill it out. It should go rather fast. Go. Then we'll just check it together.
Wait, actually, no, because just negative would be plus 0. Well, for the positive side, yeah, it's just below 3. There were like 3 negatives. The negative side, so then it's we're not finding the overall limit.
That's correct. So they'll do that on the graph. And if they just show 2 plus, you're just finding the right limit.
And it's going 3 minus.
And then here they did all 3. But again, once you answer these 2, you're done.
And not like,
Because all you do is compare them.
it's what it's close to, so your answer is 3. Instead of just like 3 minus, it's not going to, even though it is going below it. 0. He said 0. I don't know if it's ever going to ask for any of this. He said that it probably sure that it won't. So this is just what we like to think of when we're doing this. So we're thinking that it goes below 3 for the left one, and then or for the right one, and then if there was a left one. But since it's just, I don't know. It's just like we're thinking. That's just a simple answer, right? So what we do is right there. Yeah, it's just that's simple as just right. it's going with the other direction, and the other one's this direction. So
It's just on the left.
if it's
Okay, pause for a minute,
it's
look
2
up.
plus here, it is going down, but
So,
it's
everybody listen real quick.
close to 3.
Everybody just pause for a minute, look
That's
up.
what we want to know.
Your work is perfect, just look up so I can make sure you hear this. The shortened schedule issue is causing some problems, so I apologize for that. We have to get to the homework today, which is not I don't like to rush, I just hate it, but I just have to stay on schedule a little bit. So there's like 4 minutes left in class. Let me explain what's going to happen here. We're going to go through. I'm trying to think here. Hold on, because I don't want to rush you. We're going to answer this because we just finished working on it and make sure you're thinking correctly here. I wanted to have time, and this is again in a normal year I would have had time to do that, to hit these piecewise functions as an example and then kind of introduce you to what has to happen on the homework. Because of the limitations on time, I'm going to have to do kind of a hybrid approach here. I'm getting my whole Canvas thing up and running, and you've all signed up for my texting so I can communicate with you. I'm going to post some videos that I either make with other periods or I just make myself to help you kind of finish off, this page from the white packet, and then a little bit of a video to kind of help you get started on the homework itself. So watch for a text to point to the videos that you can watch at home. They'll be very short because we actually are very close. In a normal year, we'd still have 15 minutes and it would have been perfect. So I'm still adjusting to the shortened period. So anyway, back here, let's just go through this and talk together. And then like I said, I'll make the videos to help you finish. So this is the homework. And the answers to all the questions are in the back. And I've tried to make the answer, in many cases, very, very thorough. Don't ever use the answer to answer the problem. You only use the answer to verify your own thinking. But I will ask you at the start of class on Wednesday if you've done your best to get through this. If you get stuck in just a few places, don't stress too much. That's okay. If you feel like you're completely kind of lost, then you do need to come talk to me. But I will check at the start of class on Wednesday. So very quickly, somebody else just pay tally marks. Dan, please. Put it out here. Is there 3? Questions? Number 2. Let's go here. Work on name. Sorry, Jackson Center.
0.
If something doesn't look right, make sure you raise your hand. 3. Let's go Jacob Jackson.
0.
4. Let's go Daniel Flukier.
0.
Questions on any of that? And I will deliberately sometimes let somebody put a wrong answer just to see if you're really thinking, but everything there looks good.
So why would it, if you're approaching 0, why would the answer 0 not have like a 0 plus on it?
For this one here?
For 2 and 3.
These 2?
Yeah.
I know, it's perfect, Michael. It's back to the comparison between, what's happening. If the x-coordinate is really infinitesimally less than 0, you are 100% correct. The y-coordinate is going to be infinitesimally more than 0. No doubt. And the same for this. This is what you're saying, correct? However, the definition of limit is what am I infinitesimally close to equaling? So I'm not saying that when x is infinitesimally less than 0, y is exactly 0, but I am infinitesimally close to 0. So the answer to the limit will always just be no plus or minus. Is that what you mean?
Yeah.
What's your tell?
Thank you.
Anybody else? Cool. Keep going. Number 5. Let's go, Jonathan. Number 6. Oh, bell ring. Again, watch for a text, watch for videos to help you get going on the homework. Thank you. Outstanding job today. Outstanding.